Today we'll be learning about squaring the circle. But before we get into squaring the circle, let us review the basics. This is a circle, and this is a square. As we know, the area of a circle is pi r squared, and the area of a square is s squared, where s is the side length. Is there a way though for these two areas to be equal? This problem is called squaring the circle, and it has baffled mathematicians since ancient times. This problem was first proposed in Greek mathematics, with the challenge of creating a square with the exact area as a circle in a finite number of steps using only a compass and a straight edge. This task was proven to be impossible, and until now, only approximate constructions have been made. Well, what makes this problem difficult though? Since the area of the circle is pi r squared and the area of the square is s squared, therefore pi r squared equals s squared. And therefore, if we want to find the length of the square, it is the square root of pi r squared, which is equal to r square root of pi. Well, since pi is an irrational number, therefore it is impossible to make the exact side length of the square, right? That's why the problem is impossible, right? Well, that's only partly true. Take this as an example. If we want to draw a line with length square root of 2, we can just draw a right angle triangle with leg lengths 1 and 1, and using the Pythagorean theorem, we know that the hypotenuse is equal to square root of 2. Therefore, since pi being irrational isn't the problem, then what is? Well, this is where we have to introduce another classification of numbers called transcendental numbers. Transcendental numbers are numbers which are not algebraic. That means these numbers are not the root of a non-zero polynomial of a certain degree with rational coefficients. As you might have guessed, pi is an example of one of these transcendental numbers. Since we can't make an accurate construction for squaring the circle right now, we can only make approximate constructions. There are many different approximate constructions for this problem, such as this construction by Adam Adamandy Kochanski, various constructions using the approximation of pi as 355 over 113, this one by Jacob de Gelder, and this one by Srinivasa Ramanujan. Various constructions using the golden ratio, this one by Hobson, this one by Dixon, and this one by Beatrix. And Ramanujan also made this second construction. Now that I have shown these different constructions, I will show you one of the most interesting ones I have seen. The circumference of the circle is 2 pi r, and therefore, since the length of the red line is half of the circumference, then it has length pi r. Then we can extend and draw a radius, which is the blue line, and therefore it has length r. Finally, we can draw a semicircle with diameter pi r plus r. Then, after that, we can draw a half chord, which in this case is the black line. This half chord is from the tangent point of the line with the circle to the arc of the semicircle. Let this half chord have length x. When we connect the ends of the diameter to the end of the half chord, we get a right angle triangle. We know that this is a right angle triangle due to Cayley's triangle theorem, which states that if A, B, and C are distinct points on a circle where the line AC is the diameter of the circle, then the angle ABC is a right angle. This also means that the two triangles, which are marked blue and yellow, are similar. Therefore, we get that pi r over x equals x over r, and if we cross multiply, we get pi r squared equals x squared. Therefore, if we construct a square using side length x, we have created a square with exactly the same area as the circle, thus solving the problem. Although this construction does break the rules of the problem a little, it's still an interesting concept to learn. We can learn to apply Thales triangle theorem as well as similar triangles using this construction. If we were a bit more lenient in the rules of this problem, then this would be a valid construction, and we would have solved the problem of squaring the circle. But alas, the rules state that we have to draw the construction using a straight edge and compass only, and therefore the problem still remains unsolved. Well, this is all I have to show for today. I hope that you found this topic interesting, and thank you for watching, and I hope you have a great day.